Hello, I'm William Calvin, professor at the University of Washington in Seattle. The following video is tailored for somewhere between a general audience and a general scientific audience, but there are about 2 slides that are entirely optional that are really aimed only at oceanographers. You'll find, in addition, an audio-only version of this if you go to my webpage, williamcalvin.org, and you'll additionally find the PowerPoint file and the PDF file of the slides. This picture shows a bucolic summer scene in Seattle with Mount Rainier sitting there like an ice cream sundae 55 miles away. This will look rather different in the future. Most of the snow is gone by the time this picture was taken, and so what you're seeing there is the permanent ice. As many of you will know, that permanent ice is likely to be gone by mid-century. So while Mount Rainier may look white in the winter, by midsummer it will look like a deeply furrowed pile of rock. But it's not really the aesthetics of this or the gradual global warming that's been talked about so much that concerns me here. I'm going to tell you a story about why we've got a much more urgent problem and why the answer to it, carbon sequestration, must be rather big and quick. Here's just an abstract of the points I'm going to go through. Sometimes a stream of air or water discovers a new path, and climate then may suddenly flip into a new mode of operation. I'm going to go through a series of sudden shifts in climate or near misses that have occurred. To back out of the danger zone for more of them, an appropriate goal would be to remove nearly all of the excess CO2 and put it back into long-term storage, and to do this in the next 20 years. That's 30 gigatons of carbon each year. Drawdown, this would be an emergency repair, not a substitute for a low-carbon energy diet. We'll still have that problem. Chemically scrubbing the atmosphere is unlikely to scale fast enough to do this, and while doubling forests might reach the needed 600 gigatons a year, forests are not secure enough given the trends in fire and drought. We're even burning down rainforests at the moment. To avoid competing with the world's food production and therefore people, most sequestered organic carbon must come from new biomass grown in new places. Here I explore how ocean pumps might uplift nutrients and then, with other pipes and pumps, sink the new organic carbon into the ocean depths. Instead of sinking only the debris that's heavy enough to settle out, as in iron fertilization, we would be sinking the entire organic carbon soup of the wind mix layer before its carbon reverts to CO2. The CO2 produced in the depths will reach the air 400 to 6,000 years later. Spreading it out over that period greatly reduces the damaging peaks in ocean acidification and global fever. Now I'll conclude with a discussion of the various pros and cons of this approach. Our focus on the long term and on getting rid of the underlying causes of climate deterioration, while sounding logical, has become a dangerously inadequate approach by now. While deforestation and fossil emissions got us into trouble, it does not follow that fixing them will get us out of trouble. The situation is beginning to resemble locking the barn door after the horse is gone. It doesn't really recover the horse. And indeed, there's no more horse to protect by locking the barn. Second, gradual overheating is no longer the correct focus for understanding the risk we now face, where fast tracks to disaster must be forestalled. Brief peaks, whether it's temperature or high water or whatnot, usually do the damage long before changes in the average get around to it. For example, for high water, well, this is a peninsula near Galveston, Texas, that's got to be covered up by sea level rise. Obviously, temporary rises in sea level from storm surge were quite capable of doing the damage. Here's the heat wave in Europe in 2003 that killed about 35,000 people. And this just shows you the Swiss summer temperatures for 140 years and how they were distributed. And the coolest summer was in 1909, the warmest summer was in 1947. But that's the story up to 2002. In 2003, the temperature jumped off the chart. As say it is a good 6 degrees above, 6 standard deviations above the mean. Now, mind you, this is regional climate change. The global mean temperature actually didn't spike in 2003, as other areas were cooler. But there have been 8 sudden shifts or near misses in a mere 30 years on a global scale. In other words, I'm not just adding up the regional scale climate shifts like droughts and such from various places. I'm going to talk about the number of global scale climate shifts or near misses that we've had since 1976. The first one that the oceanographers and atmospheric scientists talk about occurred over the winter of 76-77. Initially the focus was on the western Pacific Ocean, but it was realized later that it was a much more global event. One of the results of it may be the way the El Nino pattern shifted. This just shows the 1950 to this year record for El Ninos. This is roughly like the temperature in the Central Pacific, but in fact it's a multivariable index. The red arrows going upwards are El Ninos. The blues going downwards are La Ninas. And you can see that up until 1976, basically La Ninas dominated. The warming El Nino events were not very large and not very long. However, after 1976, what you see is almost the flip. That is, say, the El Ninos are big and sometimes long, and the La Ninas are short and typically small. This just puts that together with what the temperature did. This is global mean land temperature, though sea surface temperature looks somewhat similar. The most interesting part of this is that you can't see an uptrend from 1950 through 1976. This was despite the fossil fuel emissions tripling during this period. The excess CO2 doubled, and the temperature, for some reason, wasn't going up. Then, certainly by 1977, it was going up at the rate of about 3 degrees per century, essentially what's been predicted for global warming for some time. The reason that you have this ramp following a flat period may very well be due to something like there's a natural control system that tries to keep the temperature constant, but then it runs out of cooling capacity. In other words, things that would help cool it in the face of these perturbations by fossil fuel emissions would be things like increased cloudiness, increased evaporative cooling, whatever. But like most air conditioning systems, there's a point at which you have saturated that capacity, and if you keep perturbing the system, now it starts going up linearly. It's still regulated to some point, but the additions now overwhelm the regulation. Now let's talk about drought. What I'm going to talk about is that from 1950 to 1982, there's not much change after 76, but during this period, major drought as a percent of the global land surface was about maybe 14%. Now, what that means is the two most extreme classifications of drought, PDSI, more than -3, for example, only affected 14% of the Earth's surface at any one time during that year. However, things changed very much at the same time as the big El Nino in 1982. Global drought doubled, and it stayed up at double for a good 15 years until the next major El Nino, when it did this, went up to triple, and stayed up at triple for about 6 years before coming back down to double. So what you see here are major excursions, perhaps triggered by the El Ninos, but not going away when the El Nino goes away. In other words, it's as if the system is latching up at a new state of having twice or triple the amount of drought that it had during this 1950 through 1982 period. This just tries to put that together with the temperature ramp and the El Nino story. What I particularly want to discuss now are some of the things that aren't shown here because they didn't happen. During the 1997 El Nino, there were big forest fires in Southeast Asia and in the Amazon. And emissions that year of the burning basically tripled. Then came back down, but in 2005, which is sort of on the end of a prolonged El Nino, there was a severe drought in the Amazon aggravated by the big heat wave in the Caribbean that created the Hurricane Alley for Katrina in New Orleans and Rita in Houston. So we've had two situations where if we had a El Nino that was twice as long, but still big. So just take either of these big 82 or 97 El Ninos and make it 1 year longer. We could have either burned or rotted most of the trees in those two tropical rainforests. And the excess CO2 from either both burning and rotting could have taken a 50% jump. That is to say, there would have been a sudden worldwide escalation of climate problems and with little recovery, because as trees try to go back in the Amazon, certainly, they never really get to trees. The ecosystem flattens out with grasslands and a little brush, and it really doesn't make it back up to trees. So that's a permanent loss of biomass into the air. Such a big burn would, of course, be a mass extinction event, losing about half of Amazon species. Similarly in Southeast Asia, home of 3 of the 6 remaining species of apes. So I've been going through here for you some abrupt shifts. There's a total of 4 to 6, depending on whether you want to count these 3 as one or not. We've had the drought one, the drought to triple, triple back to double, and we've had 4 near misses. I just told you about 2 of them, and there's 2 more coming in the later slides. That's quite a few to happen in 30 years. Basically 6 plus 4, 10 and 30 years. So we're basically every 3 years having such an event. Additional surprises, of course, could be bigger than the previous ones, we could easily spiral up to catastrophic climate change before we'd have a chance to haul it back down by technology. But most of the surprises could probably be avoided by quickly recapturing the excess CO2. This is very different now from reducing the new CO2 added to the air. This is countering that and taking back all that we've put up there. We might not have to take back all of it, but I'm going to show you the calculations for all. So it seems an appropriate goal for our emergency repair is, in effect, put the genie back in the bottle. Remove nearly all the excess CO2, put it into long-term storage, and finish, not start, but finish the job within the next 20 years. Even during that period, you'd expect a half dozen additional abrupt events or near misses. In addition to the low carbon diet we need for the long run, we need emergency repairs for the short run. An intervention that's analogous to dialysis, where you clean out the toxic substance. An emergency room patient with an aspirin overdose, well, we used to have to send them home with advice not to repeat that. We were losing about 25% of those aspirin overdose patients to heart attacks. The aspirin stirred up that kind of trouble. What we do now is to use dialysis to detoxify them. And this is basically our situation with our CO2 overdose. We need to remove the excess, the toxic substance. Considering the rate so far, it's got to have to be quick. And it's not just the half dozen, actually. There might be more because the excess CO2 has now doubled since 1976 levels. Like heart attacks, sudden climate shifts can range unpredictably from minor to catastrophic. And about the only reasonable approach to it, because there's so many different kinds of abrupt climate change, is to stop pushing the system so hard and backtrack. That means basically taking CO2 out of the air. Now this graph here just shows you emissions since actually 1750. The area under this curve starting 1950 here. Basically we have emitted 350 gigatons up through last year. And if emissions continue growing at the 3% per year rate that they have been for the last decade, we would expect another 250 gigatons to be released into the air in the next 20 years. So we have a total of 600 gigatons to get rid of. That is to say, we have to draw down, first of all, an amount sufficient to counter all of the continuing emissions. And then the green part here shows you the amount we have to draw down to get rid of the past emissions. So we need a capacity actually of about 34 gigatons a year because there's this 5-year ramp up. So that's the capacity we have to aim for. Now, what's capable of doing this? We obviously need emergency repairs that are swift and sure. And when we start looking around at how to take carbon out of the air, most of them don't look either big or quick, and they certainly don't look very secure. We need, for example, to sequester 600 gigatons of carbon, and that's about what's in the forests that remain. And of course, we could replant a lot of what was taken away over the centuries and get 600 gigatons back. However, even if you could find the space and the water to do this, the climate forecast is for more drought, more high winds, making this insufficiently secure against fire and rot. So Freeman Dyson's favorite fix, while it might have worked back in 1977 when he proposed it, is really a non-starter in today's climate with all of that doubling since then. We can't go around ignoring the other dimensions of the climate problem we now have. We can't even protect our existing rainforests from fire and drought. So how do we remove so much CO2 without doing it on land? Those schemes abound for scrubbing CO2 with proprietary chemicals like they do in submarines. Time is too short to rely upon finding the power to run such a giant new industry. But it's not necessary to remove CO2 directly from the air to reduce its concentration there. And that's because photosynthesis already removes about 210 gigatons each year in creating organic carbon molecules. Now, they capture, but of course it all goes back into the air at the end of the carbon cycle, and it's released both from respiration and from cell decomposition as biomass burns and rots. If we intercept some of the decomposition of carbon before it reaches its usual atmospheric destination, the carbon cycle becomes unbalanced and the CO2 in the air decreases via the continuing photosynthesis. To avoid competing with the world's food production and fresh water supplies, however, most of any sequestered organic carbon must come from new biomass not existing and grown in new places not existing, and then kept out of the atmospheric circulation. And I think that only the oceans are going to turn out to be sufficiently big and secure enough to do this. Our emergency repair then involves both efficiently creating new ocean biomass via fertilization or such, and efficiently sinking it into the 1,000-year depths, which turns out to be the big problem. There is lots of sinking now. You're familiar with the Atlantic submerdial overturning current that produces these two big sinks up here in the Labrador Sea and the Greenland Sea. There's also a couple of sinks, about only 1/4 the size, down in the Antarctic. Now, if you ask where the excess CO2 has already gone so far, it has accumulated in the North Atlantic Ocean. You just don't see a big hot spot like this in the rest of the world. I've cropped off to the left. Now, is that because there is more life in the ocean there? No, not really. I'm repeating it on the left here, but here's the cross section on the right, so you can see the CO2 concentration as a function of depth as you go north from the equator. And what you see above the dotted line at 500 meters depth is that there's really not a preponderance of CO2 in those near surface layers. All of the hotspots excess from the vertical inventory comes from the waters below 500 meters. That's where it's being stored. And while some of this is from winter mixing and such, most of it really is from those eddies and whirlpools that sink the surface. The largest major downwelling is that 200-kilometer wide central gyre of the Greenland Sea up at about 75 north. It rotates anti-clockwise, as you might expect, sinking surface waters. But there's a series of smaller clockwise whirlpools that form on its margin. The whirlpools are only about 30 kilometers across, but they have cores of about 5 kilometers that are really rotating like a solid object rather than a dissipative one. They are much more effective than a gyre in sinking surface waters below 500 meters. So let us look now at how to try to take advantage of this. I'm going to give you a quick look at the ocean's carbon cycle, ask what fertilization and settling out can do, and then I'll look at how to better sink the new production we create. Here is a picture of the surface layers, the it's really defined by the thermocline, that is to say the temperature starts dropping after remaining flat through the depths until you get to about 100 meters. And then below that it quickly cools because that's water that's not being carried up to the surface periodically to partake of the air temperature. What we have here at the top are the anthropogenic additions, 2 from deforestation, 8 gigatons carbon a year from fossil fuels and cement manufacture. There are, of course, other things feeding it in and out of the air from vegetation, soils, and rocks that I'm not going to discuss here. But the ocean is basically absorbing about 92 per year, but it's also releasing about 90. So the CO2 that gets absorbed, all those bubbles that the waves produce and so forth, tend to help load up the water with dissolved CO2, much of which then becomes bicarbonates. There's also carbonates, and I'll come back to dissolved organic carbon in a minute. The life forms via photosynthesis take up 48 of that 92. And they, of course, are respiring and rotting. And that puts about 37 back into the water that's going to equilibrate with the air. And only about 11 manage to settle out of this layer before it decomposes. And that's largely from fecal pellets from something as large as the larger copepods. There's also the downwelling, those eddies and whirlpools that carry water, carry the carbon from this carbon soup up the surface layers down into the depths. So these are the 2 inputs to the slow ocean circulation. Very little of it settles out, 0.01 is all. Then, of course, most of it upwells again, but there's a considerable time delay here. I'm just calling it 1,000 years, but it's really between 400 and 6,000 is the figure you should remember. Basically, the dissolved organic carbon that you get from fecal pellets decomposing and from cells breaking up can survive in the mixed layer for a month before the bacteria and sometimes coral take it up and convert it into CO2 via respiration. Now, it's worth saying here that the dissolved organic carbon in mass is 100-fold larger than the living biomass. So the bulk flow into the depths is far more efficient than any settling out. Now, once it's into the depths, it is going to turn into CO2, this dissolved organic carbon, life, the living biomass that's carried down. About half of it pretty quickly changes into CO2. Total here means includes what goes into bicarbonates promptly. The rest has about a 6,000-year residence time. And that's not because there are pockets of poor circulation. This is a widely distributed load of resistant organic carbon that apparently takes about 4 passes through the surface layers before it ever manages to get oxidized. So that's the background, and what can we do now to augment the amount that gets into the depths? Well, the first thing to consider here is augmenting this 11 gigatons a year that settles out. And we can get our necessary 30 gigatons a year by effectively quadrupling the life form in the carbon soup. As I say, we could fertilize the surface layers, as in iron fertilization, but you can do this lots of places. The only trouble is that in order to do it this way, you'd have to fertilize for 4-fold worldwide. That's an enormous amount if you're going to rely only upon the settling out of heavy debris to do the job. So unless we quickly develop a far more efficient method for sequestering the excess circulating carbon, we're back into seeing our escape routes closing off. So let's X that one out for the moment. And now ask whether we can do something about downwelling. Well, we could pipe it down, or we could augment the whirlpools. For the moment, just consider both of them together. And that, of course, is sinking not only the living stuff, but it's sinking that far more massive dissolved organic carbon. Now, this is very much like plowing under a crop. That is to say, if we fertilize via pumping up and sink nearby via bulk flow, we would essentially be burying a carbon-fixing crop, as much as farmers plow under a nitrogen-fixing cover crop. Instead of sinking only the debris that is heavy enough, we would be sinking the entire organic soup, which currently, before fertilization, is in the North Atlantic about a gram of carbon in a cubic meter. The Atlantic's radial overturning circulation, these eddies and whirlpools in the Greenland Sea and the Labrador Sea, and a few other places, currently sink about 0.6 of a gigaton of carbon per year because of that. We need to sink about 50 times as much. And so we might consider fertilizing in those areas to try to get the concentration up enough. But basically, I think we need another method rather than just using the existing circulation, which also turns out to be very vulnerable, as I'll come back to. The needed sunlight's better at lower latitudes, and so we also need an estimate now for plankton plantations that do their own fertilizing and sinking. Now, you can obviously do this with windmills, pumping up from one depth and with another set of windmill pumps that pump down to a different depth. You can also do it with a much cheaper affair, which is just basically an open pipe that has a trapdoor valve added, and it's held up by a buoy and it's weighted down by some ballast. But what this does is on the upstroke of a wave carrying this up a few meters, the trapdoor valve opens, and basically this causes the water that's inside the pipe to sort of be left behind at the bottom. It's as if it were extruded. Then on the downstroke of the wave, the trapdoor valve is going to close, and then on the next upstroke, you're leaving behind surface water in the depths again. Put the trapdoor valve swinging the other way, and you have an up pump. As say on the downstroke of the wave, the thing's going to fall with the trapdoor valve open, and that's going to leave behind deep water near the surface. So let's get an estimate now for the fertilization needed. We can use some figures from algaculture. One advantage is that algaculture minimizes respiration CO2 from higher up the food chain. And so it allows us to estimate what the minimum size of a plankton plantation would be as a percent of the ocean total, and we have to hope this is not 150%. Suppose that a mid-range 50 grams of algae can be grown each day under a square meter of sunlit surface. About half of that is carbon. That means it takes about 10 to the minus 4 square meters to grow about 1 gigaton of carbon each year. So to sink 30 gigatons of carbon yearly would require about 0.8% of the ocean surface, which is about the size of the Caribbean. So the Caribbean is not particularly where you want to do this. Space requirement might be less because you're not going to fiddle with oil-containing algal species that are very fussy about what concentrations you do them at. You're going to do it with the existing indigenous algal species, and you're going to try to sink them just as quickly as possible to make room for more to be grown. The ocean pipe spacing and the volume pumped down are going to depend upon the outflow that you need to optimize the organic carbon production's sinkable fraction. This is what's called the dilution problem in the literature. Only field trials are really likely to provide this estimate that you need to find the needed size of the plantation, the pump numbers, and therefore what's going to cost. I want to give you just one example of how you might do this. It's not so much a ready-to-roll proposal as much as a challenge, something to improve or replace, while remembering that the solution space is constrained by the need to be big, quick, and secure. And what I think this quick example shows is that a major recovery is probably still possible. So you can either pump down with windmills, or you can pump down with these pipes that bounce up and down with the waves. And I'm using windmills here in my illustration just because they're a lot easier to see than buoys. What you wind up doing is these are floating, but they're tethered together and anchored to the bottom. So the current that's flowing through this area is moving water away from us here. And so if we pump up nutrients here towards the collectors, let's say this row of pumps would be pumping plankton down, and you'd be repeating this. I've shown a fishing lane down through the middle of this, sort of a cable-free area where traditional fishing could be practiced, because this is going to attract a lot of fish, and that's respiration CO2 that you can do without. You want to keep this a decomposition CO2 matter. Remember, these are a couple of sort of optional slides. They're really aimed at the pros. One of the standard objections is the box model nutrient story. And I just want to emphasize here that what these are going to do is to form plumes that go off. And the plumes are only 20 years long. And the loop time to come back, is more like 1,000 years. And of course, very dilute by then. So you're not really having this is no steady state kind of model. This is a model of plumes, and the same is true for what you pump down. That is to say, it too is not going to come back, and if you're not necessarily going to have these two plumes interacting with one another, all you have to do is change the depths of their pipes so that what's pumped down doesn't feed back into what's pumped up. So this is, instead of box models, you basically need a Heraclitus model. That is to say, you can't step in the same river twice, is what's so different about this kind of proposal compared to the usual box model inferences. The fisheries bonus, fertilization is going to create a lot of fish. And there's some good reasons to try doing this fertilization in the major fisheries areas. They've declined an enormous amount, and even where sustainable harvesting is now practiced, it still results in fish biomass about 73% below natural levels. So there's a lot of room to improve this back up. The outer part of the continental shelf is a particularly good place to do this because, first of all, what you pump down is likely to be carried by the undertow out over the lip of the continental shelf, and it's much more likely to fall into the depths. So candidate shelf sites for all this would include the Baltic and North Seas, and also the east, the ocean that's east of the Americas and Asia. You want to note from that that these are all relatively wealthy countries that can afford to do something like this. One of the ways into this is finding the appropriate designs that would minimize getting into trouble. There's a great place for field trials, and that is there are about 4,000 oil and gas platforms in the Gulf of Mexico that are currently in operation. There are another 3,000 that were built in the past but are out of commission now. So there's a lot of room to just take an existing platform, append a pipe to it, and run the pump with whatever's handy. That you could do to gain some insight into what this is doing with the ecosystems up top and below. So here we have a candidate for removing all 600 gigatons of excess carbon by 2030. It's the sink on the spot plankton plantation that basically moves CO2 production into the 1,000-year depths. It's a local vertical loop for fertilization and sequestration that's relatively low tech, and it really mimics the natural upwelling and downwelling processes. So there's nothing novel except the quantities and the seasons in which it's being done. It has some unique advantages compared to the current climate strategies. It's big, quick, and secure, which you can't say about any of the others. It's impervious to drought and to holdout governments. It does not compete for land, fresh water, fuel, or electricity. It's what I'd like to call a cognitive carrot, an immediate payoff every year in terms of fish catch, while growing the climate fix, the 600 gigaton of carbon emergency drawdown. It does not rely upon improbable self-denial by developing countries, treaties that take longer to negotiate than to ignore, or on finding a solution to the tragedy of the commons. Questions that I get on this, answers a few of them to get us started. Is it expensive? Well, just to take the pipe pump, the wave-powered pipe pumps, it's been estimated they may cost $1,000 installed in mass production. So even 1 million of them would cost no more than the $1 billion currently spent in a single month on dog food in the US. As a policy aside, we can't afford to rely upon any one method, not even this one. So we must budget on the 1,000-fold larger scale of what an unbudgeted bank bailout might cost. What are the operating costs once you get it installed? Well, unlike fishing and farming, nothing about sink-on-the-spot plankton plantations will necessarily require handling, transport, processing, delivery, so on. Continuing costs would primarily be for maintenance and monitoring and licensing fishing boats. Won't it pollute? Well, perhaps not as proposed here. I mean, you're using local algae and nutrients in a vertical loop. But the usual considerations would apply should we want to introduce exotic or modified algal species to achieve even higher rates of sinking potential CO2. What about dead zones forming from anoxia? You'd certainly have to avoid the shallow continental shelf sites like off the Mississippi. Because of the hypoxia that occurs when you have all that biomass turning into CO2 using oxygen from the water. The fish that get trapped in one of these while it's developing, of course, get killed. And that's where their particularly bad reputation comes from. What you really need here are the plumes, the Heraclitus situation, where things are always being carried away. One advantage of windmill pumps is that compressed air could be injected into the Archimedes screw chamber that forces the water down, and to try to assure that there's sufficient oxygen available for the new CO2 production in the depths so as to avoid anoxia. There's the serious, we don't know what will happen objection, which is going to apply to anything we try, but let me try here. Fertilizing and sinking surface waters merely mimics, although in new locations or new seasons, those natural processes seen on a large scale in water mixing and in ocean upwelling and downwelling. The Earth's recovery, I might note, from the last major greenhouse episode 55 million years ago, also involves sinking the excess carbon into the ocean depths. Question, won't this just move the ocean acidification problem into the depths? It's currently a matter of surface waters. Well, there are already massive downwells to surface waters with their 30% acidity increase. Since the depths are 98% of the ocean volume, this means there's a 50-fold dilution of this acidity. Sinking 600 gigatons of carbon would only add 1 to 2% to the deep ocean inorganic carbon concentration, what affects the acidity. But that also means we cannot keep up a 30 gigaton per year sinking rate for a century without more serious impacts. Let me iterate, this climate fix is an emergency repair. It's not a model for how to do things in the future. After 2030, we should be pumping only enough to offset any remaining out-of-control emissions. As say, we'll go from pumping capacity of about 34, and we'll shut down about 30 of them, so we're still pumping, say, 4 gigatons per year. But we're going to maintain those extra 30 so that we can turn them back on again to offset any bulk burps of CO2 that you get from clathrates coming unstuck from the ocean bottom. We might want to pump an additional 2 gigatons per year to offset continuing deforestation. And additional amounts could be pumped to offset such CO2 heating equivalents as the methane leaks and the albedo loss. Question, what side effects might the pumps have on the North Atlantic's overturning circulation? Well, let me give you some background on this. Models suggest that flushing will decline about 30% on average by 2100, and this is basically because global warming's increased high latitude rainfall dilutes the surface waters so that they don't sink as well. However, just from observational stuff rather than models, the 2 major downwelling sites are already wildly fluctuating, suggesting that a major component of current climate is quite unstable. The largest flushing site, Greenland Sea, declined at least 80% in 1978, recovered in the next 10 years. The next largest, the Labrador Sea, failed in 1997 and recovered 10 years later in the winter of 07-08. Now, I can suggest a way of helping to stabilize this using the same kind of pumps. Pumping up deep water in the right places might strengthen the whirlpools. They're pumping up dense water that will then sink again. Such denser water would prime the surface waters to spiral down, and that would entrain a lot of less dense water with it, so there'd be a net gain from this. So, in summary, the 3 R's here: relieve, reverse, restore. Well, sufficient CO2 reduction should relieve heat waves and many of overheating's knock-on problems, such as deluge and drought and expansion of the tropics. In the case of acidification and of the thermal expansion of the oceans, we can talk of reversal. But in many state-dependent systems, history really matters. For example, the destabilized ice sheets that we currently are getting may continue to slide downhill even if you cool things off. Many ecosystems exhibit regime shifts, and some may prove difficult to restore. As say, once the Amazon's rainforests are destroyed, plant succession may stay stuck at grasslands for a very long time. Having squandered the 50 years since our climate problems were first discovered, we may no longer have the luxury of proceeding in the cautious manner seen, for example, with genetically modified crops. By now, it's really getting to be more like wart. The two figures in the background here and the screaming, shrieking face. Cartoonists have long exploited this, and somebody sent me this. He does have a point. Well, actually I have 4 points. What I've shown here are, first of all, abrupt climate shifts are already here and frequent. Secondly, they are like heart attacks from an aspirin overdose. Dialysis is urgently needed to head off heart attacks. Only oceans are likely to capture enough excess CO2 to do the job. And finally, only bulk flow is likely to hide enough CO2. The political leadership we need is in this voice from 300, 400 years ago. The public interest requires doing today those things that men of intelligence and goodwill would wish 5 or 10 years hence had been done. And that, I hope, is not the end. Questions, please. This has been a talk by William Calvin at williamcalvin.org. You can find the PDF and PowerPoint files, and also an audio version of this for a podcast.